to mention about the project one. Most of you did a very good job and get 100%. If some of you didn't get 100%, either because you didn't complete 3 plots, or because there was something abnormal and you didn't correct it, or you didn't explain it. You see, we're not trying to get a perfect plot. Oftentimes we don't get a perfect plot, and then you need to either observe and see if you have some way to improve the plot and to improve the efficiency of presented data. Or if you cannot improve the plot and there's still some extreme values, then you need to explain why these extreme values there. So it's not just to use the code to present the plot. It's about observing the data and then explain the data. Okay. Throughout our class, you will have to do that. So this week we will talk about the k-nearest neighbor algorithm. It's another algorithm for classification, and it supports multi-class classification for logistic regression. We said that there are only 2 classes usually, 0 or 1, right? So k-nearest neighbor support multi-classes, and it's a very easy algorithm to understand. So what we do here is, for example, there are 3 classes, okay, randomly in the space. And if we have a new class and we want to predict, then we just calculate the dot and its closest neighbor. Let me try to use this again. I have to draw a lot of pictures. It's easier. So, for example, I got a dot here. I have a value here, okay? A value here, maybe this with this x, y, z number. These all represent the different dimensions, the different features. And how do I predict this class? I just need to calculate its distance to its neighbors, and then select the k-nearest neighbor. For this one, the 3 nearest neighbor are these 3, right? And then I decide this class by the majority of the neighbors, to the majority. So the majority of this neighbor, if I use 3 neighbors, the majority of neighbor is orange. So I decide the class for this one is orange. So that's basically how this algorithm works. And here we use a Euclidean distance, which means that the distance is this direct distance, which means that the distance is x squared plus y squared and square root. There's also a Manhattan distance, which means that the distance is x plus maybe it's x plus y. Okay, that's a Manhattan distance, and usually this is the often used Euclidean distance. On to the next one. So here I briefly explained how this algorithm works. So for example, this one. In this picture, if I use a k K equals 3. What is the result of this orange? What is the result of this orange case I want to predict? K equals 3, that means that I use the 3 nearest neighbor. What is 3 nearest neighbor here? And what is the majority of these 3 nearest neighbor?
Blue squares.
Blue square. So what's the result of this case? Blue square. Yeah. That's simple. So if I do K equals, I could set up a different K value. So if I use this algorithm, I can set up a different K value. If I choose K equals 5, what will be the result of this case? Red triangles. So when the K changes, the result will be different. And how do we decide the K? Actually, toward the end of the lesson, next week, we'll explain that. You actually goes over different Ks and then choose the K with the highest accuracy. That's all we do. So let's go back to this picture. If I choose K equals 4, what will be the result? K equals 4. Think about it. If I choose K equals 4.
Yes, the blue rectangles. Since the two of them are closer than the two red triangles.
If K equals 4, that will be likely it will be these 4 cases, right? These 4 cases, right? What will be the result if K is 4? Can we decide?
The blue square, since they're closer, or
They are closer, but when K is 4, there are 2 blue squares, 2 rectangles. So actually, here in this case, when K is 4, we cannot decide the result for this circle, for this new case. So then what should we do? We should just not use 4. If there are 2 cases, you should not use the number K equals 4 because it becomes a tie between the 2 classes and you cannot decide what is the class for this new case. And same, you should not use what else number you should not use? The 6. If a 6, it could be 3 classes, 3 cases of blue and 3 cases of triangle, and still you cannot. So oftentimes, if there are 2 classes, you should not use those even numbers. And in the word, if there are 3 classes, if the target value has 3 classes, what number you should not use? You should not use 3 K equals
so about 3. 3 or 6.
Yeah, multiples of 3. Yeah, because it could be 3 different classes in the circle, and you cannot decide. It becomes a tie. You cannot decide that. Are we all good here? Question? No. So, yeah. So when you choose the K value, it shouldn't be the multiples of the number of classes. The number of classes. Next one. Can k-nearest neighbor be used for categorical variables? Here we see this is not categorical variable because they are on a different different positions. If it's a categorical variable, then this picture will be look like a x1, x2, and this maybe triangle. Three classes for x1, okay, and then two classes for x2. And if we want to predict a new case here, it's here. We try to use k equals 3. K equals 3. What will we pull up? If k equals 3, these, see, we cannot even pull up a k equals 3. It has to be 4 or 2. No. See, you cannot even pull up a k equals 3. Yeah, this one is the nearest, and then this one, these two are the same distance to the case we want to predict, right? So you could even pull up k equals 3.
You would be able to do 4 either.
Or there are two classes. I don't want to do 4. You could do check k equals 5. 5 still you cannot pull up 5. You see, if I use 5, okay, this one, you have to add this one, same. You can even pull up. So it's not very ideal if it's all categorical variable, but usually not all variables are categorical. Usually what we have is a x1 probably x1 is categorical, and then x2 is numerical. Then you could use it. You see, 1, 2, 3, and then then this will be here probably. And then it will be, then it will be easier to pull up its k nearest neighbor. 1, 2, 3, right? Oh, yeah, this will be yes. Anyway, so if it's all categorical variable, it's again it will have like a multiple options for k equals 3. You cannot pull up. However, if it has a numerical variable, then usually even if it's this one is only 0 and 1, this one is slightly different. So this x1 is slightly different between each cases, and you can still pull up the 3 neighbors or 4 neighbors. So okay, next, I think that's a basic, a quick basic explanation about this algorithm. As you see, it's really easy to understand it. And next we apply it onto a case. Okay, this is a data set about often used in prediction. in demonstration called iris data. Basically, you use the 4 variables: petal, petals, and its petal length, petal wise length, and sepal wise length to predict its target, what species of the flower it is. First, I'll load the data set and the library. And then we load the data. This is the one we data set, just load the iris, and then it will give you the data. And if you read this attribute, then it will give you just the features. And this one, it gives you the target. And here we concatenate it into a new NumPy arrays, and then you put it in a data frame. Okay, I don't want to go over these here. Just how you quickly create a data frame with the feature names and with the target. So what we got here is 150 cases, and for each case there are 4 features: sepal length, sepal width, petal length, petal width, and there's the target. Let's see the target. I believe the target has 3 classes. So it has 3 classes. Each has 50 cases, which means it's a what the word we use to require. Each target variable has the equal. Each value has the equal number of cases. If it doesn't have equal number of cases, what we say? The data set is imbalanced, and this one is balanced. Each has 50 cases. Right? And the next, what we usually do is to use a histogram to have an overview of the distribution of each feature. And you can see from this picture, you can see the range of each feature, and then the frequency of the numbers. And also you can see the target variable. It's very balanced. So this is like an ideal data set they created, but usually the target variable is imbalanced. Right? And what we have to do is to balance the data later. Next thing we want to do is what is the next thing we usually do in data prediction? We talked about it at the last lesson, and then the lesson before last lesson. What we usually do is to check the relationship.
Like for outliers.
Outliers, yeah, you could check outliers. Use box plots actually. Numerical value, numerical variables, you check outliers with box plots. And well, what you do next is to examine the relationship between the feature and the target and to see whether they are influencing the target or not. So since here, these are all numerical variables, and this is a categorical variable, what we use to check the relationship between them. Check the box plot, yeah, and what test? The test we used called
F-test. That's this one.
F-score, ANOVA test, ANOVA t-test. Okay, so let's plot the box plot first, and then we can observe to see what we find. So this is a box plot of the variable, and then its relationship to the target. What can we find from these box plots? What do you think we can find from box plots? Do they all have influence on the target, or do they not?
They don't all have the same influence.
Some
have more, some have less.
Some have more, some have less. So which ones have more, which one have less?
That would have more. The second one would have more.
Second one. What else?
The last one got the least amount of influence, maybe.
The last one,
They're furthest away from each other.
they come with
The last one had the least amount of influence, so further away.
why?
They're further away from the target.
The target is 0, 1, 2. 0, 1, 2. They're not far away from target. So this is target and this is the feature. And what we are trying to see if they have what difference between different classes. If in another word, this is a target. This target 0, 1, 2, 3 classes. 1 and 2, 3 classes, and if these box plots are all like this, what we decide.
That's not a good predictor.
That's right. Why? How do you explain it in words?
If you were gonna get the same range for all of them,
Yeah.
like what would you use? Like what kind of value would you use to get another class?
Yes. Yeah. So all people like have a heart attack or type A diabetes, type 2, type 1, type 2 diabetes, but they all drink the same amount of water. So drinking drink, the amount of water they drink doesn't affect the diabetes type. Right? So what we are trying to get what are the ideal features? The ideal features will be like this, right? Or it could be here, or it could be the top. If there's a box plot like this, what does it mean? Okay. Type 1 diabetes, type 0 diabetes, they drink this amount of water. Type 1, they drink this amount of water. And then type 2, they drink this amount of water. They're all quite different from each other. And this is a perfect feature to predict the target variable. So I can see, hey, if a new case comes at this value, we know which class it is. We know the class is so if I have a new case, I have a box plot like this. This is the target. And this is a feature, one variable. Okay, so I come a new case, and this value, this feature value is here. Then what class it is?
Most likely 0.
0, yeah, because the 0 classes are between this range. So if I come another case here, then you can quickly predict this is the class 1. So this will be like an ideal box plot to show this variable is a perfect variable for predicting the target. Here, do we see this kind of variable here in this picture? Do we have this kind of variable here?
Left one?
Bottom, yeah, left one and both actually. There are some outliers. See, there's some outliers making these two box plots have overlap, but if you take out the outliers, these box plots, they all distinguish from each other. Are very good features. So actually, I would expect that the F-score for these two will be higher for these two, because these two box plots have a little bit of overlap from each other. So what we do to testify this is the ANOVA test, right? I'll just use this code. This is the F-score. Which one's the F-score? See, these last two, their F-score is extremely higher. Although all these four, they are very good features for the target. Their p-values are all close to 0, almost 0. So they are all very, very good feature for predicting the target. But if I need to choose two, I will choose these two, because their F-score is the highest. However, there's something else we could observe from this box plots. We said at linear regression, we said if the features are very highly correlated to each other, that means x1 equals x2. Then the x2 we could discard, because x2 can be explained into x1. Do we have this kind of feature here? Do you see here, this box plot, it's almost identical, right? Almost exact the same, you see? Almost exact the same as the left one. This left and right one. They're all at this range, and then this one goes to that range.
Would the
Uh-huh.
difference on the y-axis does matter? How the right one goes from 0 to 2.5, and the other one goes from 1 to 7?
Yes, that's correct. That means that the range is different. That could be means like this one, x2 equals hey, maybe like half, 1 second, like half of this length, right? Means that this x1 equals 1 second or 1/3 of this variable. So that's what another thing we observed. These two box plots, they really look like each other. That means that these two features have correlation, high correlation. Now, what we need to do to check the correlation, just pull up the correlation matrix. And let's observe this middle part. Which ones you see have a high correlation value? Which number? That's this number here, right? 0.96, almost close to 1. Their linear, their correlation relationship is almost close to 1, right? So this one. And the sepal length, you see this one is almost 0.9. That also means that high correlation, right? Close to 1 or close to -1. That means a high correlation. And if they are in the features, then we could reduce one. We could remove one feature and reduce the dimension. So here I could remove the petal width and sepal length because they both have a high correlation with the petal length. They both can be explained in maybe a like if this is x, they both could be explained into ax or bx here. So I would choose this petal. Let the petal length stay, and then use the sepal width. These two features. Okay. 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 Next thing we want to look at is sepal width. Yeah. So my opinion stay the same from the last year. Okay. Next thing I want to explain is the feature scaling. What this means here, if we observe this petal length and sepal width, right? Let's petal width. So this one, this range of sepal width, we decided to keep these two features, and the range of this sepal width is from 0 to 4, and this range is from 0 to 8. This is fine. However, if I have another case, this x1, for example, here in this case, this x1, a range of this is a good case actually. This is a bad case. So this x1, you see, this x1 ranges from 0 to almost 0 to 1. And this x2 ranges from -10 to 50. How this will affect the distance? When we use, for this algorithm, we are calculating the distance between this dots and its nearest neighbors. This is the x2. So here, draw up this picture, okay? When we calculated the picture. When we calculate this new case, okay, this new case, and its two nearest neighbor, how can we calculate? How do we calculate the distance? We calculate the distance of this one, huh? This is the final distance of the dots and this case and this case, and this is the case to see. The problem is that this distance is dominated by which one? Which dimension? This distance is dominated by x2. This x1. Its range from 0 to 1, and this range is maybe this distance is 10. This 0 to 1 actually doesn't influence this distance at all, almost, because this number is so small, right? See, it's the distance of this dots, the distance of this Euclidean distance, it's 10 square plus maybe this one is 0.5, so 0.5 square. This dimension, it doesn't influence the final distance, Euclidean distance. And this range from 0 to 1. All these dots are close to 0 to 1. And this range, a range from maybe 0 to 10 or 0 to 20. So this distance of final distance is the 10 square plus 0.5 square. And the final distance is dominated by one of the dimension, this dimension. Are we all good here? So what's the problem here? The second feature doesn't influence the distance, right? It's useless here because this value 0.5 is just so small to the final distance value. So what we need to do is to enlarge it to the same scale. So this one also right now it's between 0 to 1, and this one we enlarge it also to 0 to 20. Then these two dimensions will have an equal weight on final disk. That's called feature scaling. You put it, you change it to one range to another range. It's like the scaling on the piano. You change it to the scale, a bigger scale.
So we take 25 to 2.
0. Guess it's still live. What we actually do here to this x2 is x2 minus X. The
screen reset.
Of course.
Oh, so what we do here is this x2, you minus this x min and divide by x max to minus x min. So see this value, it must be smaller than x max. So this value must be smaller than this one, and this final value will be between 0 to 1. Okay, so that's called normalization. There's another feature scaling feature called standardization, which is a little bit different. Standardization is if the feature follows the distribution, this normal distribution, then this mean it could be 2 or let's see another case. This distribution could be like this, okay? It still follow the normal distribution. However, the mean could be 2, or the standard deviation could be 4, and then you normalize it. You normalize it to the standard distribution with mean. You just transform this shape. Transform this shape. Transform this shape into 0, and the standard deviation is 1. That's called a standardization. So this mean changed to 0, and the standard deviation changed to 1. That's called a standardization. But for this algorithm, the algorithm k nearest neighbor, what we usually use is normalization. Use this min max min scaling. Okay. So as you see, so now after we change this scale, this was between 0 to 1, and now it changed to the equal scale. Both are on the equal scale. They have the same influence on the final distance. This is called a min-max scalar. What you do here is to pull up this function. See this function min-max scalar, and then apply this fit transform on this x. So here x, fetch the x value. So fetching the x value, discarded the other two values, and then you apply this min-max scalar, this function. Just call it norm x, okay? And then you use this function to transform this x final. And after you transform it, you can see that NumPy range doesn't have a head. Okay, as you can see, this x value, now they are all in the same range, 0 to 1. So there's no like dominant thing when you calculate the Euclidean distance.